Welcome to this presentation of the FFI RADCOM2 project, funded by Vinnova, Sweden's innovation agency. The objective of this two-year project was to enable vehicular radars to communicate, to provide fast and reliable inter-vehicle communication links, and to coordinate radar interference. The project was a collaboration among Chalmers University of Technology, Halmstad University, Volvo Cars, Magna, Chalmers Industriteknik, Gapwaves, and Comnisens. We asked the project participants about their goals and accomplishments in the project, as well as some more technical insights.
So basically we come from the RADCOM2 project, where we did modeling, simulation models, physics based on interference levels. And in RADCOM2 we assumed a single channel system, and we assumed basically ideal RF hardware. In RADCOM2 we wanted to refine the simulation models to include hardware impairments like receiver nonlinearities and phase noise, together with adding a multi-channel simulation system. So basically it's the new models we have now, where we have a multi-channel simulation model. We have modeled the receiver nonlinearities, we have the phase noise, so we can get a much better understanding of the real effects that happens in the sensor receivers while interfered, for example, or in ordinary traffic simulations. And I would say another aspect in RADCOM2 was for us to understand the impact of moving to a higher frequency band for potential future radars. So looking into the effects of 135 GHz compared to the 77 GHz. And so we have investigated and checked the propagation effects, scattering effects, and so on. And with the conclusion that there is no obvious stopper for this higher frequency band. At least there are some degradation, but it seems that it can be really suitable, at least for more closer range applications.
We wanted to investigate joint communication and sensing, which we foresee will be very useful when it comes to increasing safety in the traffic environment. Communication is necessary for collector perception. That is, to use the collected sensor data and information from traffic participants to provide better decision support. For example, on how to avoid an accident. Why not combine two services, sensing and communication, into one piece of equipment and get more from it? By participating in the project, we have gained a deeper understanding of the opportunities and challenges that are associated with JCAS, both from a hardware and a signal processing perspective. We have also studied how JCAS can be applied to different traffic situations to find out where it makes the most difference.
So the problem we saw from the Gapwaves perspective was mostly to see if we can create an antenna at D-band with the tight spacing to do the beamforming demonstration. With that comes, of course, mechanical tolerances and even seeing whether or not we could even do this. So our main outcome was making and then also measuring the antenna. We managed to create this 140 GHz antenna with our traditional Gapwave guide technology. And then we managed to characterize it in an anechoic chamber and also assembled it into our final demonstrator.
So in this project, we want to build up a 140 GHz a hardware platform for both communication and radar. And the main challenge is really to realize this with existing technology possibilities. I think the main outcome from the company, from the CIT point of view, is we really start to do the integration for the ICs and also design antenna and packaging for this very high frequency, realize the technology challenge and to see what is practical limitations to stop us to get the best performance, especially for this new frequency band for radar and communications.
We wanted to learn more on how to build and demonstrate millimeter wave RADCOM systems, if the available simulation tools and models were sufficient for the system work. RADCOM systems are proposed to use modulation methods such as OFDM. We wanted to see how this would work when implemented on millimeter wave hardware and what obstacles there are to realize these systems. Our main outcome was the experiments and the phased antenna array. The index modulation experiments show how we can realize RADCOM even with the existing and commercially available radar hardware. The phased array antenna that worked on 140 GHz is an outcome that we can build on. This was the most difficult part to implement in our RADCOM system.
At Chalmers, we are part of several large 5G and 6G initiatives where we study how we can do sensing within a communication system. In the RADCOM2 project, we do the opposite. We try to understand how can we embed communication in a radar sensing system. The main outcome of the project was our increased knowledge in terms of the radar system, including the channel model, the RCS of the targets, the antennas, the hardware, and the impairments of the hardware. We also studied the impact of different modulation formats and waveforms on sensing. And in particular, we demonstrated index modulation over FMCW radar with data rates up to 800 kilobit per second. We also studied the trade-offs between sensing and communication in such a radar-centric ISEC system. And we've done this in the spatial, temporal, and frequency domain.
Here's a small overview of the results from the antenna design for the RADCOM2 project. Our antenna has been designed with a certain set of specifications. Starting off with the aim to do beamforming at large angles, we need a spacing of the different elements around half a wavelength to avoid degrading lobes. Secondly, the realized gain is quite important based on the link budget calculation, where we need at least 12 dB. Furthermore, we are aiming at a large impedance bandwidth from 130 GHz to 140 GHz to be able to still change the frequency of the actual active circuitry. And besides this, we also need to include our mechanical features such as cruise, as well as a radome, which is an option to use for the outdoor testing which was planned. The antenna element has been designed in a small section of the final antenna array, where we have simulated a board in the center and two of its neighbors to have a good environment of how the antenna is going to behave in the end. And here in this result you can see that the return loss is well below minus 10 dB, even minus 15 dB in our frequency band of interest. And we also already get some indication on what kind of mutual coupling we get to the neighboring antenna elements. To be able to connect our antenna design together with the rest of the RADCOM2 project, we need to connect them together in a more standardized fashion. And in the RADCOM2 project, the WR6 waveguide dimension has been chosen. And here you can see the design of the transition which goes from the rich gap waveguide onto this WR6 waveguide. Again, nice return loss below minus 15 dB in the entire frequency range. Since we're working at such a high frequency, the mechanical tolerances do quickly become a problem. To be able to ensure that the final antenna is working properly, we have to do a tolerance analysis on the different components to be sure that if the mechanical part is slightly different than the design, it will still function properly. The return loss of our antenna is one of the more important characteristics for this project, since the loss will also impact the link budget. Therefore, we have measured a handful of the prototype antennas we've built, and in this plot you can see 3 antennas and there are 4 of their channels each, which stay below minus 10 dB return loss in the entire frequency range. Also, the radiation pattern is a very important spec for our antenna. And in this result you can see the simulated beamforming of the antenna with its 4 channels. So we have measured the radiation pattern in an anechoic chamber in a passive way, and then later in post-processing we have been able to add the different phase shifts to the different antenna elements to be able to show the results. And here we can see that our antenna allows beamforming from -50° up to 50°.
Chalmers Industriteknik is one of the partners within FFI RADCOM2 project. Within the project, the main contribution from Chalmers Industriteknik is to develop hardware solutions for radar and communication demonstrator at 110 to 170 GHz frequency band. The main contribution from CIT lies in 4 different areas. First is the MMIC design and the packaging. Together with Chalmers, we have developed the silicon germanium-based transmitter and receiver chipset, so to say MMIC, and also another variation with a gallium arsenide mixer are also used in the module. As we can see on the left-hand side, we developed the no bonding wire non-galvanic waveguide to silicon germanium chipset interfacing, and also made the manufacturing validation. The module is tested within the project, and also gallium arsenide based mixer modules designed, fabricated, and measured, and used as a transmitter mainly within the project. Together with this part of work, we have provided active circuit for the system demonstrator in the project. The second part work is MLW multi-layer waveguide fan-out structures. With the implementation of the project, we noticed the connectivity waveguide for antenna beamforming in the system would cost a lot to purchasing just the waveguide connections, and we made like low-cost, high-performance multi-layer waveguide fan-out structure, as shown on the 3D pictures, provided beamforming antenna connectivity to different transmitter and receiver modules, and this was used in the final demonstration. The third part of the work is we have made 7-layer multi-layer waveguide antenna at 130 GHz. The antenna is featured 3 cm by 3 cm, and this was verified together with a Gapwave used as a low-cost solution, especially towards the automotive industry. Finally, Chalmers Industriteknik, working together with the Gapwave and Halmstad University, has set up the full demonstrator of radar communication hardware modules within the Halmstad University as a final demonstrator.
Hi, my name is Emil Nilsson, and I'm going to present the RADCOM hardware modeling and measurements. I'm going to talk about nonlinear simulation model of RADCOM system, and joint radar communication channel model, and multiple antenna model and measurement. Nonlinear simulations are important because analog electronics presents unwanted nonlinear response that may create ghost targets that obstruct detection of real targets. Also, the radar waveforms we investigate, like OFDM, are sensitive to nonlinearities. 2 different simulation tool chains have been investigated: System View and MRT, which are Keysight tools, and SPR Plus and Emit, which are ANSYS tools. Full hardware simulations have not been possible to do due to insufficient data for the hardware parameters. None of the tool chains fully solves the modeling task, so the proposed solution is to combine different tools. We have combined SPR Plus and MATLAB, and SPR Plus and System View. Both allows for arbitrary waveforms. We believe that SPR Plus and System View allows for maximum tool integration. This is what it may look like in System View. With the channel model to the left, we have delays and attenuators modeling the different signal paths. The block in the middle is the hardware, is the hardware, where we have possibility to introduce nonlinearities. To the right, we have the interface to the simulation tool. And this is an example of constellation diagram, and to the left is the constellation diagram has passed through a linear system, and to the right through a non-linear system, and we can see that the response is slightly warped to the right. Here we have an example of a radar scenario with a pedestrian between two vehicles. The radar sensors of the vehicles interfere with each other. In this case, we can see no difference when we have the linear response or the non-linear response. The antenna simulation and measurements are based on a 4-element array. To the left, we can see individual measurements of the return loss, and we have a good performance, better than 10 dB of the band. To the right, we can see the field of view. It's ±40 degree in azimuth, and we have a focused beam in elevation. This is the setup for the beam steering measurements. To the left, we have the antenna array with 140 GHz up converters integrated. To the right, we can see the array sitting on the turntable, and we use an LNA and down converter to receive the signal from the array. Before the measurements could be formed, we have to manually adjust the signal levels of the transmit channels. After that, we could confirm that simulation and measurement agrees. And here we can see measurement of several steering angles. And with this setup, we could modify it to do radar measurements. We know that we are close to the sensitivity to detect a pedestrian. We did this setup, and we used FMCV signal with a bandwidth of 800 MHz. You can see the expected leakage between transmitter and receiver at 0 meters, and it has a peak width that corresponds to the bandwidth. But we also see a spurious response that we could not get rid of. We believe it's from the millimeter wave hardware. We have also confirmed that by changing from the 140 GHz front end to 80 GHz front end, to confirm that it's not the digital electronics or the signal processing that introduces this spurious response. The conclusion is that we have found different simulation toolchains for nonlinear joint radar communication systems, that the system work requires better models and data for the millimeter wave hardware, and that we can electronically steer the beam of the 140 GHz array antenna.
Chalmers studied integrated sensing and communication from two perspectives in the FFI RADCOM2 project. We have considered both the communication-centric and the radar-centric viewpoints. In the communication-centric viewpoint, we rely on standard communication waveforms such as OFDM and reuse them for monostatic sensing. Sensing can be opportunistic, based on transmitted data, or optimized, based on tailored pilots. In the radar-centric viewpoint, we rely on standard radar waveforms such as FMCW and augment them with communication data. These two approaches lead to different trade-offs. The first trade-off is in terms of the performance. As you can see, all waveforms have similar radar sensing capabilities if they use similar time-frequency resources. However, they vary greatly in terms of communication rate. This may indicate that communication waveforms are preferred overall. However, in the second trade-off, we show how hardware-friendly each waveform is. This hardware friendliness refers to the peak-to-average power ratio and the requirements in terms of the ADC bandwidth, for examples. Here we see a clear benefit of radar waveforms which are designed to be hardware-friendly. We can combine these trade-offs and evaluate the trade-off between communication rate and hardware friendliness. Not surprisingly, the more rate you want, the more expensive hardware you will need. Among the different studies we conducted, we analyzed the radar and communication performance in different realistic environments using the CARLA simulator. CARLA is an open source simulator for autonomous driving research, which we use to generate automotive scenarios. We also defined communication and sensing parameters, which we then combined in MATLAB to determine the radar and communication performance, which was then again visualized in CARLA. Here is an example showing where vehicle 1 senses vehicles 2 and 3. The different plots represent the range profiles at different times, showing the effect of interpath interference. For more information and technical results, we refer to our published papers, which are linked below.
Hi, my name is Carl Vanes and I work for Volvo Cars. Together with my colleagues Stella, Sara and Iman, we have worked with radar simulations and post-processing in the RADCOM2 projects. And now I shall go into some of the highlights of the work we have done. So first of all, we have worked with a simulation of nonlinearities. We have focused on modeling of phase noise and the receiver nonlinearities. So first we have the phase noise. So the phase noise components are added in the post-processing after the ray tracing done in ANSYS. So the higher peaks in the range Doppler map is identified and phase noise is added to these peaks. And this is done by reconstructing the transmit and receive signals corresponding to the peaks and add the phase noise components to these signals. And by using this method, we get the appropriate behavior of the phase noise with the range-dependent characteristics that can be seen in the example down here. We have also simulated receiver nonlinearities, and to do this we have used the third-order polynomial model with the input like receiver gain, 1 dB compression point and intercept points for the second and third order. These have been taken from available data sheets for automotive radar mimics. And to confirm the correctness in the simulation, we use a two-tone input signal to get the intermodulation products for second and third order intermodulation to see that these end up with the correct levels. Then we take these models into a traffic scenario. In this case, we have simulated a Euro NCAP scenario with a car to bicycle near side adult upskirt. In this simulation, we have simulated a front right corner radar with 1 TX and 4 RX antennas. And on the bottom you can see the range Doppler map for this simulation. Next investigation is propagation of the signals. Here it's the purpose to compare the difference in propagation between the current 77 GHz radars to potential future radars at the higher center frequency of 135 GHz. So for this comparison we have used static scenarios from RADCOM1, and we have similar characteristics for antenna patterns and waveforms between the 77 and 135 GHz simulations to get comparable results. So here we have one example with the scenario: 2 vehicles front towards front with a pedestrian in between, and we have the results for the 77 GHz and the results for 135 GHz. And what we can see is the attenuation of the target increases when moving to the higher center frequency. You can also see in this scenario that the interference level reduces with the higher center frequency. Next is an investigation regarding radar cross-section. So here we have also compared the scattering effects of targets between 77 GHz and 140 GHz. We have used two different targets, a pedestrian and a vehicle target. And for the pedestrian target, we have modeled it both like a perfect electrical conductor, but also with a dry skin properties. And here we can see the results from 77 GHz and 140 GHz for the pedestrian target. And the result is that the average RCS is approximately 1 dB lower for both the pedestrian and the vehicle target when increasing to 140 GHz compared to 77 GHz. Last, we have the scattering point extraction for extended target simulation. So here we take the scenario simulations done in Carla by Magna and interface that with the ANSYS ray tracing to get a better channel and scattering simulation results as input to the Chalmers sensor model to get the output data as communication and radar performance metrics data. So here is one of the use cases used where we can see a video of the scenario and the scattering point extraction. So we take the scenario configuration from Carla, input it to ANSYS AVX that generates ADC data, and then we do post-processing to the FFT CFAR direction of arrival estimation to end up with this detection list or the extended point scattering of the two targets. And this detection list is then fed to Chalmers models to get the results for radar and communication meters.
Within the RADCOM2 project, simulations have been a useful way to explore how joint communication and sensing technology relates to traffic situations. First of all, we have the use cases, which are important to highlight the advantages of JCAS. The goal of the use case simulations is to show how the communication and sensing would work in a realistic scenario. For example, what would we do with the ability to direct communications, and what accuracy and resolution would the sensing get? Some situations found in the use cases relate to obstacles, or traffic participants seemingly suddenly appearing like e-scooters or cyclists. Sharing information about vehicles braking can prevent rear-ending. Overtaking is also a potentially dangerous situation where JCAS could increase traffic safety. Last but not least, reliable automated valet parking can be very convenient. Example, the vehicle with JCAS detects a pedestrian, which may be difficult to do in the dark, and can share this information. There are many things to consider before you can get started with simulations. In this project, we were several participants from different organizations and companies at different locations. Therefore, we chose a modular approach in steps, as opposed to an agent-based one. Here, the Carla simulator was used to get the information about the vehicle dynamics from which coordinates and directions were extracted. Then, each participant could apply their models and share results, which were collected and visualized in Carla. In order to get useful simulation results, each component of the model must be designed to suit its purpose. These are examples of models that were used in the system simulator. Sensing and communication have been in focus, but they required knowledge about the signatures, the antenna properties, and the wave propagation. While the goal of the modeling may be to describe a system, it also forces you to really think about how the system works and how it can be useful.